and you can start whenever you are ready. Thank you.
Sure. Thanks, Minka, for the introduction. Thanks for inviting. It's my great pleasure to give this talk online. So today I'm going to talk about the turbulence in outer protoplanetary disks. My collaborators, Eleonora was my summer intern and have been working with Henrik, Minkai, Xuening, and Gordon on various projects. So let's start from some background introduction on the ionization of protoplanetary disks. So we're looking at the thermal and non-thermal ionizations in the disk. The thermal ionization is primarily passively depends on the temperature of the central star. So if we go to the very inner region of a disk, say less than 0.1 AU, then the temperature is high, and then the gas are fully ionized. So the gas and magnetic fields, they are coupled very well, and we're in the ideal MHD regime where we can have the magnetorotational instability operating in this region. But if we go further out in the disk, say larger than 0.1 AU, then the temperature is low, so the thermal ionization is weak. And also the non-thermal ionization from X-rays, far UVs, and the cosmic rays, they're also weak. So in general, in a large portion of the disk, we have very low ionizations. And we need to invoke non-ideal MHD effects to describe the gas dynamics in the protoplanetary disks. So there are in generally three non-ideal MHD effects in total: the ohmic resistivity, the Hall effect, and M-polar diffusion. The M-polar diffusion dominates at strong magnetic field and low densities. The ohmic resistivity dominates at low magnetic field but high densities. The Hall effect is in between them. So in a realistic disk, you will find the M-polar diffusion dominates in the outer region of the disk and near the surface of the disk. The ohmic resistivity dominates at the midplane and at the inner region of the disk, and the Hall effect is in between them. So in this talk, I'm going to focus on the outer region of the disk. So the M-polar diffusion is a dominant non-ideal MHD effect. So we know that the ionization fractions in the disk is weak. So traditionally, the magnetorotational instability, which is considered as the primary source to drive accretion, does not work very well. And it is found that the magnetized disk winds dominate the angular momentum transport in protoplanetary disks, which leaves the main disk body laminar. So this is a little problematic because we do need some weak turbulence to confront observations. And in outer disks, there are two possibilities, two instabilities that can induce this weak turbulence. The first one is the magnetorotational instability. Although it's weakened, we can still have some weak turbulence driven by the MRI. The other possibility is a number of hydrodynamic instabilities that can induce turbulence, and which I'm going to focus in this talk is the virtual shear instability. It is one of the most promising hydrodynamic mechanisms that can drive turbulence. So let's start with the MRI. To study the MRI, we conducted global 3D non-ideal MHD simulations with Athena++. So we're focusing on the outer region of disk. So we incorporate M-polar diffusion in the simulations. The simulation domain, we have R spans from 1 to 100, theta from 0 to pi, and we're simulating a wedge. So the azimuth domain spans from 0 to pi over 4. We use static mesh refinement, so we achieve a resolution of 32 cells page in R and theta, 16 cells page in azimuth. There are three parameters in this simulations. We have M-polar L-Sesson number, which parameterizes the M-polar diffusion strength. This AM, when AM is large, we are more in the ideal MHD regime. When AM is small, we have strong M-polar diffusion. The other parameter is the magnetization in the disk, which we use plasma beta, defined as the gas pressure to the magnetic pressure. and the fiduciary value is 10 to the fourth. And the last parameter is the cooling time scale in the disk. And for this MRI simulations, we use tau, the cooling time scale, on the order of 1 local orbital time scale. Later you will see the VSI simulations, which the cooling time scale is very short to in order to have the VSI onset. So I'm going to show a movie for our fiduciary simulation. On the right panel is the radial velocity. The middle panel is the meridianal magnetic field. You can take it as vertical magnetic field at the midplane. And on the right-hand side is a azimuthal magnetic field, B phi. Going to play the movie for another time. So you see that as time evolves, on the left panel you see some MI turbulent going on, developing there. And then if you look at the middle panel, the vertical magnetic field, you will find that those vertical magnetic fields, they are concentrated at certain radial locations in the disk, right? And this phenomenon is very interesting, and I'm going to detail that in the next few slides. So this plot is, the color is the strength of the vertical magnetic field. X-axis is the radial locations in the simulation, and the y-axis is the time evolution in the simulation. So you find that different panels are for different ampoule diffusion Alsace numbers. So you'll find that for all these models, the magnetic fields are concentrated into magnetic flux. Some of them are rather wide, thinner, some of them are wider, and you can see some of them are static, some of them are propagating radially over time. So this magnetic flux concentration can lead to radial gas surface density variation. What I'm going to show is a movie. The y-axis is the gas surface density, x-axis is the radial locations in the disk. Different colors are for different simulation models, for different ampoule Alsace number and for different magnetic field strengths. And you see that this radial gas surface density variations are developing, right? So why this magnetic flux concentration phenomena is important is that the rings and gaps are so frequently commonly detected in protoplanetary disks by ASIAA, and there are quite a few mechanisms can drive these rings and gaps. We have the most popular, the planet-disk interactions. The magnetic field, the flux concentration can also drive these rings and gaps because these rings could correspond to the surface densities, the high surface densities, and the gaps might correspond to the low surface densities in this movie. And especially this mechanism is appealing for early types of disks where massive planets may not form yet. So that's for the magnetic field, magnetic flux concentration. We're also looking at the mass accretion and turbulence levels in the disk. We find that the angular momentum transport is primarily dominated by the magnetized disk planes, though the MI turbulence can make some minor contributions to it. The turbulence level in our fiduciary simulation with m equals 1 is reaching 0.01 of the local sound speed, and we find a dimensionless alpha parameter on the order of 10 to the minus 4 driven by Reynolds stress and 10 to the minus 3 driven by Maxwell stress. And since this is a 3D simulation, we're also looking at the azimuthal plane. And we find that the magnetic fields and the surface density profiles, they show asymmetry. So no vortices are found in the simulations. It's possibly because the relatively narrow phi domain adopted in our simulation, or it can also because of the magnetic fields that can prevent the bending of from the vortices. That's pretty much I want to talk about the MI simulations. Now I'm going to jump to the vertical shear instability that can drive turbulence in protoplanetary disks. So there are a number of hydrodynamic instabilities that can drive turbulence. We have vertical shear instability, also convective overstability in its linear regime, and subcritical baroclinic instability in its nonlinear regime, and we also have zombie vortex instability. So the onset of these instabilities depends on the thermodynamic conditions and disk stratifications. Taking VSI as an example, we need very rapid cooling, and the rotational velocity, the angular velocity should vary over height to excite the VSI. So on the right-hand side is the plot showing the active zone of the VSI and other hydro instabilities. We see the VSI is in green, and it spans pretty much from several AU to 100 AU. So that really covers the entire outer region of the protoplanetary disks. So the instability criteria I also already mentioned a bit. We need vertical shear gradient, the omega dz, and another condition shall be met is fast cooling to remove the stabilizing buoyancy effect. I'm going to show a movie for the VSI in hydrodynamic simulation just to show how does VSI look like in its nonlinear state. The saturation of the VSI is dominated by this large-scale, remarkably coherent vertical oscillations or motions. Okay. So the vertical shear instability is initially discovered in the context of differentially rotating stars back to 1960 by Goldreich, and it is until recently Nielsen applied that to protoplanetary disks. He conducted idealized hydrodynamic simulation for the VSI and found the VSI can emerge sustain in his simulations. Then people add more and more physics to the hydrodynamic simulations, such as radiative transfer, and then people did 3D simulations, and they find small vortices can emerge in the atmosphere plane. Since protoplanetary disks are the birthplace of planets, we also have dust particles embedded in the disk. So once we put dust particles in the simulation, we find the vertical oscillations of the VSI can stir up the dust particles. And once we have the dust back reactions, the VSI working together with stream instability can concentrate the dust particles into these bright strips, as shown on the right-hand side. So in a realistic disk, the disk is embedded by magnetic fields. So we wonder how does magnetic field affect the VSI. The first series of this work is conducted by Henrik and Papalouise. They did the linear analysis in a local incompressible shearing sheet model with ideal MHD. The plot I'm showing here on the left, the x-axis is the B field strength, y-axis is the kx, the radial wave number, kz is the vertical wave number, and the color is the growth rate of the instabilities. We see that in the yellow region corresponding to the magnetorotational instability, MI, and on the top left region, it corresponds to the VSI. And in this plot, in the ideal empty regime, we find that the maximum MI growth rate is much higher than the VSI growth rate. The MI prefers relatively strong magnetic field, but the VSI prefers relatively weak magnetic field. That means the VSI can be suppressed in ideal MHD when we have strong magnetic field, right? This is not good because once we have stronger field, then the VSI cannot emerge in the disk. But if we add some non-ideal MHD effects using resistivity as a proxy, we see that. So the middle panel here, x-axis is the kx over kz, y-axis is the magnetic field strength, color is the growth rate again. So we see that once the resistivity is weak, then the MI is strong, the VSI is weakened. But once we have stronger resistivity, we find that the MI is suppressed and VSI is revived in this regime. So that is good because in the realistic disk, in the outer region of the disk, once we have a stronger M-polar diffusion, then the VSI can be revived in this regime. So now to consolidate the linear theory, I conducted 2D non-ideal MHD simulations for the VSI with M-polar diffusion. This movie on the left panel is density, middle panel is the meridian velocity. This the vertical velocity and the midplane, and on the right-hand side, I have the azimuth magnetic field. So we see that in non-ideal MHD simulations, the saturation of the VSI is very similar to what we have seen in hydrodynamic simulations. This is consistent with the linear theory, because once we have M-polar diffusion, we have non-ideal MHD effects, then the VSI can be revived. Just to go into play movie for another time. Okay, so that's a 2D simulation. To study the MI and the VSI together, we further conducted 3D simulations. The simulation setup is very similar to the simulation setup of the MI simulation I showed. The difference that now we have a very fast cooling time scale, so we can extract the VSI in the simulations. The plot I'm showing here, they have different M-polar diffusion strengths. So on the right-hand side, the M-polar diffusion is weak. So the MI can operate, and we do see the MI turbulence in the disk region. On the left-hand side, the M-polar diffusion is strong, so it can kill the MI, and the vertical shear instability now dominates the disk region, as we can see this characteristic VSI vertical oscillations taken over. And in between them, we find that the vertical shear instability and the magnetic rotational instability can coexist. So in all the simulations, the mass equation, the angular momentum transport, is also dominated by the magnetized disk winds. For the turbulent velocity on the left-hand side, for the VSI, turbulent disk is on the order of 0.01 of the local sound speed, and on the right-hand side for the MI turbulent disk is stronger, it's on the order of 0.1 of the local sound speed. Alpha parameter for AM equals 1 model reaching 10 to the minus 4 and 10 to the minus 3 for Reynolds and Maxwell stress respectively. Another important result I want to address is that even for the VSI turbulent disks, we find this magnetic flux concentration phenomenon can develop, and also this reduce surface density variations. So we can see rings in the gaps even for with VSI turbulent disks. Okay, so that's VSI with MHD with magnetic fields. Now we're going to get rid of magnetic fields and back to hydrodynamic regime to study the saturation of the VSI. So we have seen that the VSI, the saturated state of the VSI, is dominated by this large-scale coherent vertical oscillations. So this is a little problematic because the length scale of this saturation pattern is a bit too large. So by the Kolmogorov theory, we expect that the turbulent will be cascaded down to very small scale patterns, which it can be dissipated. But what we see now is large scale turbulent eddies. So how can we get this small scale eddies for the VSI? Henrik and I proposed a saturation route by a parametric instability. You can call it wave-wave interactions or resonance if you like. And so just to explain what is a parametric instability, this is a clip for a swing oscillation system. And we see, so there are actually two frequencies or two waves in this movie. So the first one is the oscillation frequency of this swing, and the second one is the guy is pushing this girl. So there's a forcing frequency from this guy, right? He's pushing this girl periodically. And when these two frequencies match, the girl can get to higher and higher. But if the guy is pushing too slow or too quick, then the girl will almost stop. So from this movie, we can see that once we want to have this wave-wave interaction or resonance, we want the frequencies to match. And in a two-wave coupling scenario, here it's just the first frequency matches the second frequency. So omega 1 equals omega 2. And in the VSI problem, we have three waves in the system. And for the three waves to couple, we need the frequency of the first wave to equal to the sum up of the frequency of the second and the third wave. So it's just omega 1 equals omega 2 plus omega 3. Okay, so we wonder what are the three waves in the VSI problem. For the omega 1 is the VSI wave. For the omega 2 and omega 3 here, there are inertial waves in the protoplanetary disks. So VSI is actually an overstability. It's an unstable inertial wave. So VSI, we can treat it as a wave, and it's going to be omega 1. Or we can call it primary wave. So the VSI wave can go in resonance with another two waves in the protoplanetary disks. They are inertial waves. If you don't know inertial waves, that's fine. It's like we have sound waves in the air. We also have other waves in the accretion disks, and the inertial waves are one type of these waves. And we call this inertial waves secondary waves, and the energy can transfer from the VSI wave to the inertial wave, just like in the swing oscillation system, the energy transfer from this guy to the girl. So the guy here is the primary wave, he's the VSI wave, and the girl here is the inertial wave, the secondary waves. So the secondary waves can grow exponentially by obtaining the energy from the primary wave, right? So it becomes unstable. This is like the girl gets higher and high because the energy transfer from the guy to this girl. So we did some math, we did some derivations for this parametric instability in the paper. So tedious, don't want to go through that. What I'm going to show is a 2D simulation. It's a local simulation, incompressible. And then we use spectra called Snoopy, so Fourier modes as orthonormal basis. And the initial condition for this simulation is that we have a VSI wave. So we have one VSI wavelength in both X and Z direction. And for simplicity, we just take the wavelength of the in the X direction for the VSI equals the wavelength of the in the Z direction of the VSI. And the resolution is about 64 cells per wavelength in both directions. So this is a local simulation, so it's really a small patch in our global simulation. And this is the result from the simulation. So we see that when t equals 0 is just our initial condition, it's a VSI wave. But as time evolves, we see that the inertial wave, the secondary waves, are emerging. And finally, the secondary waves, they take over, dominate the gas dynamics in this local sharing box. And we see these inertial waves, they have a shorter wavelength, right, compared to the initial VSI wave. Just to compare the linear theory to our simulations, I'm plotting here x-axis is the time, y-axis is the Fourier amplitudes of selected wave modes. So the black curve here is the VSI wave, and the red and blue curves are for secondary inertial waves. So we see that as time evolves, the VSI wave, the Fourier amplitudes of the VSI wave is dropping over time. So this energy gets into the secondary inertial waves, right? Because we see that the amplitudes of these two inertial waves, they are increasing over time. So the secondary inertial waves grow exponentially. They're unstable, so that's why it's an instability. And then the energy of the VSI waves transports to this secondary inertial waves. The inertial waves have narrow wavelengths, right? Because we see their wave number is large, so that means the wave number is large. The wavelength is shorter, and that is good because that makes this VSI pattern small scale, which is easier to be dissipated in by the viscosity in the disk. If we want to resolve this parametric instability in a global simulation, it probably will require very high resolution to capture them, and we estimate that it's nearly 3,000 cells per age resolution needed. Well, we didn't conduct the global simulation by ourselves because it's very time consuming, it's very demanding numerically. But last year, there's a paper on the VSI doing the resolution study, and with the highest resolution reaching about 200 cells per age. Leads find that in their simulation, in the RZ plane, in the meridian plane, they find these small vortices emerge on top of the large-scale vertical oscillations of the VSI. So this is very interesting, right? Because it might be the evidence of this secondary inertial waves excited by the parametric instability. So I guess that's all I want to talk about in this talk. I was thinking to talk about something about the debris disk, but I got 3 talks this week, and it's really, I don't have enough time. So I guess I will just stop here and take any questions. Thank you.
Okay, thank you, San, for the great talk. We have plenty of time for Q&A if anybody has any comments or questions from the audience. Any questions? Okay, maybe I can go first. So I was wondering, because the parametric instability in this VSI business, I mean, the simulation you did was spectral, right? So, and the spectral method, obviously, I have a intrinsically higher resolution than grid-based codes. So in the spectral simulation, you had 64 cells. So if you have so you need 64 cells to resolve it. So that translates to, you think, 300 cells for a typical grid-based code. I'm just wondering how the
Um,
resolution translates between your spectral simulations and the typical grid-based
yeah.
simulation.
So how we estimate the 300 cells per age is not actually from this spectra code simulation. So we estimate the wavelengths of the VSI in current global simulations. See how many
Okay.
wavelengths of this VSI wave can have in one age. And we found that it's around 10. We have 10 wavelengths per age for this VSI wave. And then to have the parametric instability, because you can see that the wave number for the secondary inertial waves, they are like the wavelength is like three times or one third smaller than the VSI wave. So that means that is one third of the wavelengths you're seeing
Okay.
here. So then we say, oh, maybe we need 10 cells to resolve resolve one wavelength of the parametric instability wavelength scale. So that's how we estimate.
Mhm. Okay. Okay. See.
Mhm.
Yeah, 300 cells is actually quite tough. Yes.
Yeah, so
So
that's
I
pretty.
was curious. So you explained how the primary VSI wave excites I guess the smaller scale inertial waves. But do you expect those to excite even smaller scale, like the cascade to keep going?
Yeah, yeah,
Is that what's expected?
yeah, indeed, we actually expect like the inertial wave cascade. I guess we can have even smaller scale inertial waves excited until like it's reaching the like the length scale of the viscous length scale of the disk.
Okay, let's see. Okay. Anybody else have questions or comments for Jaitan's talk? I thought it was great, but I've heard it a couple of times actually. So yeah, sorry to keep asking questions, but
Yeah.
in the MHD plus VSI simulation, so you mentioned that even with the non-ideal MHD simulations, you still had this flux concentration.
Mm-hmm.
Um, so yeah, in slide 23 here, so this still happens even if it's non-ideal MHD. But here you also have VSI, right? So I'm wondering in these flux concentrations, is the VSI suppressed in these rings? Right?
Uh, No, not so if we look at this plot, right, on the left-hand side is for the VSI turbulent disk, then well, I guess you're asking because if you put dust in this simulation, then the dust will be concentrated at this pressure bumps, and then it can suppress the VSI. But in
Oh no,
our
I was
simulation,
actually
mm,
I was just thinking because you mentioned in the first part of your talk that a strong magnetic field should suppress the VSI. So I was wondering if
mm,
in those
right.
flux concentrations you have a strong B field, should that suppress the VSI?
Yeah, it's probably not strong enough, or because we have ample diffusion here, um, we don't see the size pressed at this pressure bumps. It's very interesting. Um, so you can
Okay,
have this
thanks.
flux concentration, but then you still have VSI operating very well.
Okay,
Hmm.
okay. We have a question from Idrani. Das, one of our new postdocs. Please go ahead.
Yeah, thanks, Ken. Nice talk. So I was wondering, could you please explain me again that how does the magnetic flux concentration leads to the rings and gaps, the substructures of the disks?
Yeah, um, so we um that's a good question because we for physically we don't really well we don't so I don't know how does this magnetic flux leads to the to this radial variations in the disk. But just look at the simulations, then you will find that you'll find this gas surface density variations corresponds to the formation or the generating of this flux concentration. So there are some relation between them. There are a couple of mechanisms proposed for the magnetic flux concentration, and that may relate it to how you get this gas substructure, but it's not. So those mechanisms, they vary over different simulations. The flux concentration phenomenon is robust, but the maximum is still a question.
I see. So, I mean, do you think, I'm just thinking widely that, do you think that the one reason could be the magnetorotational instability? Could that also cause the magnetic flux concentration? I mean, could that redistribute the magnetic flux all over the protoplanetary disk so that maybe the surface density is getting accumulated at some point or something like that?
Yeah. Yeah, so we actually look at so we look at the flux, the flux developing over time, and we actually find it's the non-ideal MHD component is the ampolar diffusion that drives this flux concentration instead of ideal MHD, because you would expect the magnetorotational instability is induced in ideal MHD regime, but it's actually the non-ideal MHD effect that leads to this flux concentration in our simulations.
Okay, thanks.
Thank you.
Thank you for the question. We have a question from Wei Han. Please go ahead.
Can you hear me?
Yeah.
Okay.
Yes, please go
I have
ahead.
a question about I have a question about your parametric stability. As I remember, the parametric is basically the material equation, in which states that the driving force has a 2 times larger frequency of the characteristic frequency. However, your result shows is the space has well generated the half wavelength amplitude. Is correct? How and my question is how to connect it, because my new question is describe the dynamic system is related to the time evolution. However, your result is about the spectrum, the wavelengths. How to connect this to how to connect the parametric to your result?
I guess I don't get the question. Can you rephrase that a bit, or sorry, I don't get the question.
My question is your result is the how to say that is K wavelength is a space resolution. It's described to is K equal to 2, the amplitude will grow. It's your figure shows that.
Mm-hmm.
However, you say that is the parametric instability. However,
Right.
if you need this instability, it says that you need couple the K equal to 1 amplitude to the K equal to 2. So you can increase it. But however, I cannot find this coupling in your equation. Can you explain how to you connect these two to use the parametric instability to explain your result?
Right. So the condition here I'm showing is just for the frequency, and for the parametric instability, the other condition is that you need K1 equals K2 plus K3. Okay, so that's how you get how you find the relation between those case of the secondary inertial wave and the primary wave. So yeah, I'm sorry, I didn't show the other condition, but you also need their wavelength match in the system. Yeah, thanks for the question. Yeah.
Yeah. So sorry, I cannot get your idea because I didn't see how to connect the wavelength relation in your equation, in your
Right.
evolution.
So this equation showing here is just for frequency, right? It's not for the wavelength. But for
Yeah.
this parametric instability to happen, you need another condition for the wavelength, which I'm not showing here.
Oh.
Yeah, so you need K1 equals K2 plus K3. So that's how you get the wavelengths of, how you predict the wavelengths of the secondary waves.
Okay. Oh, I see. Okay.
Yeah, so I'm sorry about that.
No problem. Okay. Thanks.
Thank you.
Thank you. Thank you for the question. Pingao, you have a question? Please go ahead.
Yes. Yeah, I have naive questions. The first
Yeah.
question is when people see these concentration in magnetic fields, then usually people will think that's a buoyancy or Parker instability. So I'm just wonder if why all these effects are not observed in your simulation.
Is that as a buoyancy?
Or Parker, Parker.
Well, I guess in this context, people didn't mention this buoyancy Parker instability. What they mentioned, the mechanism, is probably one of them is like due to the reconnection of the magnetic field at the midplane. That's one possibility. Another possibility, there's a secular wind instability. But again, there's no consensus like which one really drive this flux concentration in the simulations. I feel like it depends on the resolution people use. If the resolution is low, then they can have some reconnection at the midplane, and that can drive the flux concentration. In some paper studying this MI turbulence. But in our simulation with high resolution, we find that it's actually due to the 9D MHD effect. It's due to the ampolar diffusion that drive this phenomenon.
Okay.
Yeah, but I guess the mechanism is a bit complicated here. We didn't really look at that in our paper, but we do the analysis and we know that it's the contributions from 9D MHD effect rather than the ideal MHD effect.
Okay. So may I have a second quick question? So this so when you consider the VSI plus the magnetic field MRI, and can you see this the vortex forming
Yeah,
in your simulation? Yeah, because VSI alone from your presentation, you show they can produce the small vortices. I'm just wondering if for the magnetic field and will kill the vortex or not?
Yeah, that's a good question. So we don't see any vortex in this simulation for the VSI turbulent disk, and also either for VSI turbulent disk or for MI turbulent disk. So I think the magnetic field actually kills the vortices that can emerge for the VSI.
Okay, thank you very much.
Thank you.
Thank you, Pingao. If there are no other questions, let's thank Cui-san again. You can use this little applause emoji to give her a round of applause for her talk. And yes, thank you. Okay, yeah, thanks to Cui-san for the great talk. and I will be closing the session right now.
Thank you.
Thank you.
Thanks, bye.